Video should allow you to identify redox reactions. When we're done, we're going to make a very, very easy summary of this, but I want to show it to you first, and then we can find a very, very simple summary. So if it's a redox reaction, you have to have one thing that loses electrons. Let me just write E's here. And you have to have one species that gains electrons. So some reactant has to lose electrons, some reactant has to gain electrons. The one that loses electrons is getting oxidized, and the one that gains electrons is getting reduced. Make sure we remember, if it's getting oxidized, the number is going up, it's increasing. If it's getting reduced, the oxidation number is going down. And again, that makes sense because if you're gaining something negative, electrons, your charge is going down. Now, let's start with things that are not redox. I think if we get those out of the way, we can identify redox reactions very easily. So everything on this page is not a redox reaction. And I've got two things on this page. The first thing I have are physical changes. Whether you're dissolving something or melting or changing its phase, those are physical changes, and those are not chemical reactions. And redox is a type of chemical reaction. So what happens when NaCl, let's say, goes to NaCl liquid from the solid that it was? Oh, the Na is still +1 in the compound, and the chloride is still -1. Nothing was no electrons were lost or gained. All we did was we melted salt. All right. Now, NaCl could be dissolving as well. Well, what happens when sodium chloride dissolves? Well, we've seen these pictures before. The Na plus sticks to one side of the water molecule, right? And the chloride sticks to the other side of the water molecule, and opposites attract. It's a partial negative and a partial positive here. But look at what we started with. We started with a positive sodium ion +1 and a chloride -1. And when we finish the dissolving process, we still have sodium ions, Aq now, but they're still sodium ions +1. And we still have chlorides, which are still -1. So during whether it's changing a phase or dissolving, that's not a redox reaction. So be careful and look for that in choices. Now, there is one specific type of chemical reaction which is not a redox reaction, and that is a double displacement. And there's two types of double displacements. There's between ions in aqueous solution, and acid bases are also a type of double displacement. They're usually put under the general term metathesis, but you can just think of them as double displacement. So for the first one, what we have is we have an acid reacting with a base. I'm near a church, obviously. I don't know if you can hear that, but I can. Anyway, so when the acid reacts with a base, you always get water and you get a salt. Now, we were always able to predict what the products of these reactions were because the charges on the ions, okay, within the compounds would never change. So we would be able to figure out that the barium chloride compound forming was this, and that's because we assumed that the barium stayed +2. Sorry about that. And that the chloride stayed -1. So if this is +2 and this is -1, we get the formula BaCl2. Nothing changed the oxidation number. There were no electrons lost or gained. If we had a double replacement in which we had this insoluble precipitate, in this particular case, we would get AgCl. Now, the reason why we're able to figure out the formula for AgCl is we assume that the chloride stays -1 and the silver ion stays +1. And because we have these charges, which we now call oxidation numbers because the same thing for ions, we get that formula of AgCl. And then we know that the other compound we're going to make is going to be KNO3. And we know that because the nitrate was -1 to start with and the K was +1 to start with. Now, I'm not bothering to find the oxidation number of the nitrogen in there, but we talked about this. We know that within a nitrate, which is on both sides of the reaction, the nitrogen always has the same exact oxidation number. In this case, it happens to be +5. Right? So we could do that. We could do like x - 6 = -1, and we find the nitrate was +5, and it's +5 wherever you see a nitrate. So what reactions are redox reactions? Well, all the reactions on this page are redox reactions, and there's one that's particularly special at the bottom, letter E, which I decided to add at the last second. That's why it's all in blue. And what I've done here is I've put the obvious oxidation numbers up here already. Like, so all the elements are 0. All the alkali metals are +1. All the alkaline earth metals are +2. The aluminum, when it's in a compound, is +3. The hydrogen is +1. And I've left out some of the oxygens and other elements that we have to figure out or discern. Okay, so let's see if we can go through these. Chloride is always -1. What you want to see here is this chloride is going from -1 to 0. So it's going up on the number line, isn't it? It's not as negative. It's becoming more positive. It's losing electrons. So you have one thing that's oxidized, and you have the sodium going down from +1 to 0, and it's being reduced. Now this is a decomposition reaction, and many decompositions, but not all of them, are redox. HCl plus Mg, this is a single replacement reaction. The H is going from +1 to being an element by itself, so it's going from +1 down to 0. It's being reduced. The magnesium is going 0 to +2. It's going up in number. It's being oxidized. The aluminum is going from 0 to +3 because it's an element over here, but it's in a compound over here. So it's going up in number. It is being oxidized. The O2 here is going from 0 to -2, and it is being reduced. And before you finish these, let me point out an easy trick, and please pay attention to this trick. If something is on one side as an element, and on the other side it is in a compound, it's probably going to be redox. There's a couple of weird exceptions to that, but the general rule is if you see a chemical reaction which an element is by itself on one side and then a compound on the other side, and it's not something that's confusing like dissolving, which looks a little like this but is not, it's a redox reaction. All decompositions in which you make elements are going to be redox. All single replacements, because you make an element gets kicked out. When it was in the compound, it had a number to it. When it's outside the compound, it's 0. So when you react hydrochloric acid with magnesium, you get hydrogen gas. The fact that you're getting the element hydrogen tells you the element hydrogen has a different oxidation number than it did in the acid because it was +1 in the acid. It's redox. In the synthesis, if you start off with 2 elements and you make a compound, the 2 elements were 0. They're not 0 in the compound. It's redox. Combustion always has oxygen by itself. The oxygen by itself is 0. It's not going to be 0 in these compounds. Right? So over here, the carbon, okay, you have 4 + 1 hydrogens, which means the one carbon to balance it out has to be -4, right? Because, right, we did that, right? This is like x, +4 = 0. What's x equal to? On the other side, this oxygen is going to be -2. The oxygen is -2, except in peroxides, which we don't have here. Oxygen is -2 in water. So the oxygen is not changing its oxidation. The oxygen is changing its oxidation number. It's going from 0 to -2, which tells us the oxygen is going down in number. It's being reduced. And the carbon started out as -4 over here. And on the other side, since it's with two -2 oxygens, the carbon over here has to be +4 to make this neutral. So the carbon is going way up. It's going from -4 all the way up to +4. It's being oxidized. Now the last one's an interesting. Now notice once again though, you have an element by itself, element by itself, element by itself, element by itself, element by itself. Right? When you see that, you're pretty much sure it's going to be redox. And the last one is too, but I just want to show you this because this does show up on the regents. I don't know. Well, I'm trying to teach you at this point redox. We'll talk about the non-regents later. But I would like you to at least understand redox before you move on and do something different. This is called a disproportion reaction. I'll write that down. Disproportion. In a disproportion reaction, the same substance gets both reduced and oxidized. That might seem weird, but take a look at this. This is hydrogen peroxide right here. And we did this. We did the elephant toothpaste demo where the fluffy stuff came out of the test tube and made a huge mess. All right. Also, somebody won the Miss United States or Miss America pageant doing this demonstration. It's on video on YouTube. Anyway, in this particular case, the oxygen is not -2 because the balance off the 2 + 1s, each of the oxygens in there have an oxidation number of -1. Now watch what happens. In water, the oxygen is -2 like it always is. The only time oxygen is not -2 is in peroxides and in one compound called OF2, or as an element by itself where it's 0. So watch what happened here. The oxygen, some of the oxygen atoms went from -1 to -2, and some of the oxygen atoms went from -1 to 0. The ones that went from -1 to -2 went down in value, and so they were reduced. So some of the oxygen in the peroxide was reduced and is now in the water molecule. And some of the oxygen, okay, that was inside the hydrogen peroxide is now free oxygen, the elemental form, with an oxidation number 0. In that case, it went from -1 up to 0. So some of the oxygen was actually oxidized. But you still have this thing to see. You have an element by itself on one side where it isn't by itself on the other. So the bottom line is if you want to find a redox reaction, make sure it's not a physical change, make sure it's not a double replacement. As long as you see an element on one side and it's in a compound on the other, you can rest assured it's going to be a redox reaction.